Welcome to section 4.2, reduction of order. Objective number 1, understand the concept for rejection of order. Rejection of order is a technique used to find a second linear independent solution to a second order homogeneous differential equation when one solution is already known. Given a known non-trivial solution, y sub 1 of x, of a second ordered homogeneous differential equation, we can seek a second solution, y sub 2 of x, such that y sub 1 and y sub 2 are linearly independent. To ensure linear independence, we are going to assume y sub 2 is of this form. Y sub 2 of x equals u of x and times y sub 1 of x, where u of x is an unknown function to be determined. Substituting this into the differential equation transforms it into a first order equation in terms of u of x, which is easier to solve. So now let's take a brief detour just to look at solutions to non-constant coefficient second order differential equations of the following form. A sub 2 of x times y prime, double prime, plus a sub 1 of x times y prime, plus a sub 0 of x times y equals 0. In general, solving these type of equations is significantly more challenging than solving equations with constant coefficients. However, if we already know one solution to the differential equation, then we can use reduction of order to find a second solution. So while reduction of order is useful, finding the first solution is often the hardest part. So in many cases, the process of determining the first solution also provides the second solution, making reduction of order unnecessary. However, when we do have the first solution, then this method, the reduction of order, provides a systematic way to obtain a second independent solution. So now let's look at an example. So given that y sub 1 equals x squared is a solution of x squared y double prime plus 2xy prime minus 6y equals 0, use reduction of order to find a second solution, y sub 2. So first we're going to put our differential equation into standard form. So when we do that, we will be dividing each term by x squared, which would get us y double prime plus 2 times y prime divided by x, because the x will cancel, minus 6 times y over x squared equals 0. Okay. So now we want to find the form of y sub 2. And to do this, we're going to make a substitution. So we're going to set y equal to u times y sub 1 and find its necessary derivatives depending on what's present in our standard form dE. So y is then going to equal u times x squared, because y sub 1 is x squared, which was given to us. When we take the derivative of this equation, we will get u prime x squared plus 2 times ux. We will also need the second derivative, so we're going to take the second derivative of y, and we will get u double prime x squared plus 2xu prime plus 2u prime x plus 2u. When we combine like terms, we'll get u double prime x squared plus 4u prime x plus 2u. Okay, so now we have y prime, y double prime, so we can substitute these expressions into our standard form of our dE. So when we do that, I will insert the expression for y double prime. I'll then insert the expression for y prime and for y. Okay, so now I can simplify this dE, and I would get y double prime x squared plus 4u prime x plus 2u plus 2u prime x plus 4u minus 6u. Combining like terms then would get us x squared u double prime plus 6xu prime equals 0. Okay. All right. So now that I have substituted in my y, my y prime, and my y double prime, I can use substitution like w equals u prime, in order to make my DE a first order linear differential equation. And then I can solve it using the steps we've learned thus far for linear equations, or linear differential equations, to be more specific. So when I substitute W for U prime into my DE, I'll get x squared W prime plus 6xW equals 0. Okay. Now I want to write this in standard form, so I'm going to divide all terms by x squared so that I have W prime by itself. So that would get me W prime plus 6W divided by x equals 0. So now I can follow the steps for solving a first order linear differential equation. So we're going to find the integrating factor, I of x. So finding I of x, we know that's e to the power integral of p of x. And so our p of x here is 6, 1 over x, d of x. And so when we simplify this integral and then apply it to the power of e, we'll get x to the 6. So now I'm going to multiply each term in my DE by x to the 6. So when I multiply W prime plus 6W divided by x, each term by x to the 6, I'll get x to the 6 W prime plus 6x to the 5th W equals 0. Okay. This then can be written as the differentiation of x to the 6 times W equals 0. So we're going to then take the integration of both sides. When we do that, we get x to the 6 times W equals c. Getting W by itself, we'll divide both sides by x to the 6. Okay. Now we know W equals U prime, so I'm just going to substitute back in my U prime. Okay. And then I'm going to take the derivative. So du equals cx to the negative 6 dx. Take the integration of both sides, and I'll get u equals negative 1/5 c sub 1 x to the negative 5th plus c sub 2. Knowing that negative 1 over 5 c sub 1 can be combined into just one constant c, so I'm going to now rewrite u as c sub 1 x to the negative 5th plus c sub 2. Okay. So we knew our original substitution was y equals u x squared. So that means u is going to equal y x to the negative 2. So substituting that into my answer from my integration, I'll get y times x to the negative 2 equals c sub 1 x to the negative 5th plus c sub 2. Dividing each term by x to the negative 2, my second solution is now y equals c sub 1 x to the negative 3 plus c sub 2 x times x squared. Okay? And so that's using the reduction order in order to find our second solution. But now we can generalize this into a formula that makes the process of finding our second solution just a tad bit simpler. So in our second objective here, we're going to use the general formula for reduction of order. So a second order differential equation in standard form, so that's y prime plus p of x times y prime plus q of x times y equals 0, where p of x and q of x are continuous on some interval, has a second solution given by y sub 2 of x equals y sub 1 of x times the integral of e to the power negative integral of p of x d of x divided by y sub 1 squared of x d of x. Okay, so we're going to use this integral times y sub 1 of x to get our second solution. So this is the second method for finding the reduction of order. Okay, so we have a function here, y sub 1 equals x squared, and it's a solution to this dE x squared y prime, double prime, minus 3x y prime plus 4y equals 0. And we're supposed to find the solution on the interval 0 to infinity. Okay. So the first thing we're going to do, we're going to rewrite this in standard form. So that means we'll be dividing each term by x squared. That will give us y double prime minus 3 over x y prime plus 4 over x squared y, which equals 0. Now we're going to use that general formula to help us find y sub 2, so our second solution. So first, let's identify our p of x and our y sub 1. Both are unknowns that are needed in that general formula. So our p of x, according to the standard form, is going to be the negative 3 over x, and our y sub 1 was given to us in the directions, and so that equals x squared. So knowing these two, we can then plug it into the general formula for reduction of order. And so now we then need to simplify and evaluate. So in computing the integral, let's first look at the e to the power integration 3 over x d of x first. All right, so we're going to compute that integral. So e to the power integral of 3 over x d of x is going to equal e to the power 3 natural log x, which then simplifies to x cubed. Okay, so if we substitute that back into our general formula, we would then get x squared times the integral of x cubed divided by x to the 4th d of x. Okay, we can simplify x cubed divided by x to the 4th, and that would get us 1 over x. When we then evaluate this integral, we then get x squared times the natural log x plus c. If we distribute that x squared, we then get x squared natural log x plus x squared times c. Okay, so the general solution of our dE would be y equals c sub 1 times x squared natural log x plus c sub 2x squared. And so this then would be the second solution to our dE. And this provides a more systematic way to finding your second solution when one solution is already known. Alrighty. Well, that concludes the end of section 4.2. Enjoy.